Welcome back to the deep dive. Today we're jumping into a really fundamental calling in sport. How does the human body actually move? And, why?
Exactly. We're doing a deep dive into simple biomechanics. So for any of you out there revising for your exams, think of this as your technical breakdown.
Yeah, we're going to be looking at the absolute building blocks of movement. So things like the principles of force and then the mechanics of levers inside the body.
And the goal here is to give you those aha moments. We want you to really get why an athlete's body moves the way it does when they say launch from the blocks or throw a javelin.
So we've got a twofold mission. First, we'll hit the big picture, the external forces, Newton's laws, all that good stuff.
And then we'll zoom right in, we'll look at the levers inside the body, and we'll use a really simple tool, the FLE 1-2-3 rule, to classify them and understand what advantage each one gives.
Okay, let's get into it. The absolute first principle, force.
Yeah, and it's actually kind of simple when you boil it down. In physics, force is just a push or pull. That's it. It's what makes things change.
Push or pull. Simple.
Yeah.
And the moment that push or pull actually causes a change in motion.
That's when you bring in what is, well, probably the most important rule in all of sports mechanics, Newton's second law.
The law of acceleration.
The law of acceleration. It defines the whole relationship between how much force you apply and how much you speed up. And the formula, the one you absolutely have to know, is phi dollar times a way.
Force equals mass multiplied by acceleration.
Right. And what that means for an athlete is pretty huge. If you want to accelerate, so speed up, slow down, change direction, you have to apply what we call a resultant or an unbalanced force.
Okay, so if the forces pushing me forward are bigger than the forces holding you back, like air resistance.
You accelerate. It's that simple. And if the forces holding you back are bigger, you decelerate.
So that formula, phi dollar equals m times a. Let's talk about the m, the mass. If a winger in rugby wants to get faster, is it just about dropping mass or is it all about the F generating more force?
That is a brilliant question. And it's all about balance. I mean, yes, a lighter athlete needs less force to accelerate. The M is smaller.
Right.
But in almost every sport, the real focus is on maximizing F the force output from your muscles. Look at a shot putter. They're huge, right? But that mass helps them generate incredible force.
So it's a trade-off. You need enough muscle mass to create that big push, but not so much that it becomes, well, dead weight that you have to accelerate.
Precisely. It's the core dilemma the formula imposes on every athlete.
Got it. Okay. So when an athlete applies that force, they're not acting in a vacuum. There are other forces at play. Let's break those down.
Yeah, there are 4 critical ones you need to be able to define and apply.
Okay. I'll take the 2 that are always sort of working against you.
Go for it.
First, you got gravitational force. Your weight. It's the constant downward pull. Anytime you're in the air, gravity's trying to bring you back down.
Unavoidable.
And second, air resistance or drag. That's the force that opposes you as you move through the air. You see cyclists and skiers getting into those tuck positions all the time to minimize it.
Exactly. Now, for the 2 forces the athlete is actually, creating or using.
Right.
You've got the action force, which is your muscular force, the internal push from your muscles contracting, and then you have friction, which is the force between 2 surfaces, like your shoe and the track.
And we often think of friction as a bad thing, but you need it to push off, right?
Oh, absolutely.
Yeah.
Without friction, you'd just be slipping on the spot. It's essential.
Okay, so that interaction, the muscular push, the friction on the ground, that brings us to the real engine of movement. Ground reaction force, GRF.
This is it. And this is where Newton's 3rd law kicks in.
Law of reaction.
The law of reaction. For every action, there is an equal and opposite reaction. It's so fundamental. When a runner pushes down and back on the ground,
That's the action.
the ground, because it's so massive, it pushes back on the runner with an equal and opposite force. And that's what propels them forward.
So let's take a basketball player trying to jump. To get a bigger upward force from the ground, what do?
Well, they have to apply a bigger downward force into the ground. That's the action. They bend their knees, they swing their arms down, all to maximize that push.
So the harder and faster they push down.
The harder and faster the ground pushes them up. The ground reaction force has to be greater than their own body weight for them to even leave the floor. That action-reaction pair is everything in locomotion.
That is such a clear way to put it. Okay, so that's the big picture. The force is acting on the whole body. Let's zoom in now, inside the body, to the machine itself.
Yes. Let's talk about how the bones and muscles work together as levers.
Because every single movement, whether it's nodding your head or kicking a ball, is a lever system in action.
It is. And every lever, no matter what, has three essential parts. You have to be able to identify them.
Okay, the FRE trio. I'll list them. You define them in the body. F.
Fulcrum. That's the pivot point. In the body, the fulcrum is always a joint.
Yeah.
Resistance, sometimes called the load. That's the weight you're trying to move.
Yeah.
Could be your forearm, could be a dumbbell.
And E?
Effort, that's the force your muscle applies. It's always where the muscle inserts or attaches to the bone.
Okay, fulcrum, resistance, effort. Joint, load, muscle.
Got it. Now, how do we classify them? Because there are different types, right?
3 types. And the memory tool you need is the FLE 1-2-3 rule.
FLE 1-2-3, I like it.
It's all about which of those 3 components, F, R, or E, is in the middle. It's that simple.
Okay, let's do it. First class liver, what's in the middle?
F is for first. The fulcrum is in the middle. The setup is effort fulcrum resistance, like a seesaw.
And the classic example in the body is the neck, specifically balancing your head. The fulcrum is the joint where your skull meets your spine. The resistance is the weight of your face trying to tilt forward.
And the effort is from the neck muscles at the back, pulling up to keep it stable.
Precisely. And its main advantage isn't power or speed, it's balance. Keeping your head steady so your eyes can track things.
Makes total sense.
Yeah.
Okay, on to the second class lever, so following the rule.
R is in the middle, the resistance is in the middle, the order is fulcrum resistance effort.
And the body example for this one.
It's the ankle when you do a calf raise, going up on your tiptoes.
Okay, walk me through that. FRE.
The fulcrum is the ball of your foot on the ground. The resistance is your entire body weight acting down through the ankle joint. And the effort comes from your big calf muscle, the gastrocnemius, pulling up on your heel via the Achilles tendon.
I see it. And just looking at that setup, the effort is being applied much further from the pivot point than the load is.
And that's the key. That gives it a huge mechanical advantage. It's built for power. It lets a relatively small muscle force lift a very large load, your whole body. It's why it's so important for jumping and pushing off.
Right, so first class is for balance, second class is for power, which brings us to the last one, and the most common one in the body. Right.
By far the most common, the third class lever.
So E must be in the middle, effort is in the middle, fulcrum effort resistance.
You've got it. And the classic example is the elbow joint during a bicep curl. The fulcrum is the elbow itself. The resistance is the weight in your hand, way at the end. But the effort, where your biceps muscle attaches to your forearm, is really close to the elbow.
Oh, wow. So that's the complete opposite of the last one. The effort is now really close to the fulcrum, and the resistance is far away.
Yes. Which means it has a terrible mechanical advantage. It's inefficient for force. To lift a 5-kilogram weight, your biceps has to generate way more than 5 kilograms of force.
So why? Why is this the most common design in our body if it's so inefficient at lifting?
Because of the trade-off. What you lose in force, you gain in speed and range of motion.
Ah.
Think about it. A tiny, fast contraction of the biceps muscle near the elbow results in the hand moving through a huge arc, really, really quickly. It's perfect for throwing a ball or swinging a tennis racket.
So the body is choosing speed over raw strength in most of our limbs.
Exactly. It's a compromise. We sacrifice force efficiency to be able to move our hands and feet quickly over large distances. And in sport, speed is very often the name of the game.
That's fascinating. Okay, let's quickly recap everything we've just unpacked there.
Good idea.
We started with the basics. Force is a push or a pull, and its effect on movement is governed by Newton's second law. Y$ equals man times the watt.
Right. To accelerate, you need that unbalanced force.
Then we looked at the specific forces, gravity and air resistance holding you back, and muscular force and friction pushing you forward, which led us to ground reaction force.
And Newton's third law, the action-reaction pair that makes all movement possible.
And then we zoomed in on the body's internal machinery, the levers. We learned the 3 parts, fulcrum, resistance, effort, and the crucial FLE 1-2-3 rule for telling them apart.
Which gave us our 3 distinct functions. First class, like the neck for balance.
Second class, the ankle for power, high mechanical advantage.
And the most common, third class, the elbow, which sacrifices power for incredible speed and range of motion.
Understanding that trade-off is it's key to analyzing why athletes move the way they do.
It really is.
Okay, now to leave everyone with a final thought to chew on. We've just established that the third class lever, like your elbow, gets its speed because the muscle attaches so close to the joint. Your hand might be moving at 30 meters per second when you throw a ball.
But the point where the muscle is pulling is moving much, much slower, maybe only 1 meter per second.
Exactly, a huge difference. So here's the question. Because that muscle insertion point moves such a tiny distance to create that massive, fast movement at the hand, what specific demand does that place on the muscle tissue itself?
Oh, that's a deep one.
Yeah. To generate that much force that quickly over such a short distance, what does the muscle have to be exceptionally good at? Is it about the speed of contraction, the number of fibers it can fire at once, or something else entirely?
That's the hidden cost of speed. Thinking about that will definitely take your analysis to the next level. So review the formulas, remember those lever examples, and you'll be set.
Happy deep diving, and we'll catch you next time.